This video is part of a series in which I describe how to implement a simple microcontroller core in System Verilog. In this video, I'll be taking a look at the basic instruction fetch and execute cycle, and I'll introduce the finite state machine that will control our core, focusing on the timing that applies to all instruction execution. This diagram shows the general module organization of the FPGA we're designing. Each rectangle in this picture is a System Verilog module. Here's the core module, which contains the finite state machine we'll be discussing today. In previous videos, I've described a number of these other modules, including the modules that store the program and the data, as well as the 8-bit registers. We've also got a couple of combinational modules. One is for decoding instructions, and another is for the arithmetic logic unit. In a Harvard architecture, the program memory and the data memory are separate, as shown here, while in a von Neumann architecture, we have just a single unified memory. As I've mentioned, the EveCore architecture can be implemented either with the Harvard approach or with the von Neumann approach. And in our design, we're going to take the von Neumann approach. So we have just a single memory, and we have a module called simply memory, and that will store both the program and the data. We've also got some Verilog registers. We've got an 8-bit instruction register, which will contain the opcode of the instruction that's currently being executed. And we've got a 16-bit program counter and a 16-bit stack pointer. And we've got a register that contains the state of the finite state machine. So, by the way, from here on out, I'm going to be using the word register to refer to System Verilog registers, and I'm not going to be talking about the 8-bit registers of the EveCore architecture itself. So now let's look at a timing diagram to see how our finite state machine moves through states. In this diagram, I'm showing the three registers: the state register, instruction register, program counter, and the clock signal. Whenever we load a register, it will always be on the rising edge, or the positive edge, of the clock, as shown here. We've got a number of different states, and these are equated to symbolic names. And so we've got a start state, we've got fetch, execute, execute 2, execute 3, and so on. Every instruction always begins with a fetch state. Some instructions take only one state, some take two, and others take 3 and 4, and so on. Whenever they take more than one state, the states are always done in the same order. It's always fetch, execute, execute 2, execute 3, and so on. Now here we're looking at an instruction that apparently takes 3 cycles, or 3 states. And it starts with the fetch state, and then it goes to an execute, and then an execute 2 state. And we're also seeing the program counter, and I want to point out here that there's an offset. The current program counter during this instruction's execution is 1 greater than the address from which that instruction came. So previously the program counter was 7, and we fetched a byte from address 7, and that is instruction 7. At the same time, we're incrementing the program counter, so here it is 8. And so while instruction 7 is being executed, the program counter is 8, and it will remain 8 throughout the instruction unless we have some sort of a call or branch instruction, in which case we might modify it. But we won't worry about that right now. So we see that the program counter and the instruction register are loaded when we go into the fetch state, at the same moment we go into the fetch state. So let's get rid of this clock because we don't need to see that. And let's next look at this combinational signal called next state. In my diagrams, I show registers in green, and I show signals that are computed combinationally in blue. And we are loading the state register, always loading it from this combinational signal that we compute called next state. So part of the work of executing an instruction is to compute the next state. So when we're in the first state of the instruction, that is the fetch state, we determine that we need a second state, so we set the next state to exec, and then on the next clock pulse we go into that state. And then looking at that same opcode, while in the exec state or the execute state, we see that we'll need yet another state or another cycle. So we set next state to 2. And then in the last cycle of this instruction, we look at the opcode and we know that it just needs 3 cycles. So we can now go into the fetch state. And we always see the same pattern in both the next state and the state register, right? Except it's offset by 1, as shown here. Many instructions take only a single cycle, and we see an example of that here. We're going from fetch state to fetch state to fetch state, and we see that the program counter is incremented on every clock pulse. We also see that the instructions are offset from the program counter by 1, as we saw before. Instructions are kept in memory, so now let's talk about how we're going to interface to the memory module. First of all, we're going to supply an address to the memory module in 1 clock cycle, and it's going to take 1 cycle for the memory to produce a result. So on the next clock cycle, we'll get something out of the memory module. Unfortunately, this is a little bit too late to load the instruction register. Right? If we're going to load this register, say on this clock pulse right here, we need to load it from data that's available in this cycle right here. So this is too late. So how are we going to solve this problem? Well, first of all, let's introduce another register, which is called instruction save. This is an 8-bit register. And what we're going to do is we're going to copy or load it from what comes out of the memory. Whenever we have a fetch cycle, okay, so on every fetch state and no other times, we're going to be loading the instruction save register with whatever came out of the memory, like we've shown here. So what happens is we take our program counter and feed it combinationally into the memory unit, and then on the next clock cycle we get a byte out of the memory unit, and then on the following clock cycle we're going to load that into the instruction save register. So now what we're going to do is, instead of having a register for our instruction, we're going to change that to a combinational signal, and we're going to compute it from both memory out and instruction save. And we'll use code like this. So when we're in a fetch state, like right here, we will use whatever just came out of the memory. So we'll use the memory output. Otherwise, in all other states, exec, exec2, and so on, we'll use whatever we just saved in the instruction save register. And we will be loading the instruction save register if and only if we are in a fetch state. So we have this code here. So here we see it happening again. At the end of this instruction, we've got the program counter being fed into the memory. And then on the next clock cycle, we get a byte out of the memory. And then on the following clock cycle, we load it into the instruction save register. And using the memory output on the fetch cycle and the instruction save register on the other cycles, we can compute combinationally the value that we want to use for the instruction. And the instruction will drive everything else. So we'll be looking at the current state that we're in and the value that's in the instruction register. I guess I shouldn't call it a register because it's combinational. But we'll be looking at the current instruction as well as the state to determine all of our other signals, like what our next state should be and what we feed in to the memory address. Typically, we'll increment the program counter when we go into a fetch state, and then it will stay the same. But on some instructions, as I mentioned earlier, call and jump instructions, we might be doing some other things, and we may end up feeding a different value into the memory on the last state of the instruction. But this is the typical pattern that we see. So the next question is, how do we get started with this? So when we reset our FPGA, we're going to load the state register with a special state called start. And we're going to load the program counter with 0. And we will feed the program counter combinationally into the memory unit. So here's our very first clock pulse. And on that, we'll be fetching from the memory. And it will come out of the memory in this cycle right here, and that's exactly what we showed before. So we just start executing at this point. And from the start state, we always go into the fetch state next. We've also got a situation where sometimes we have a problem. For example, we might have an illegal instruction. And so for that, at the very first state of the instruction, namely the fetch state, we see that we've got a problem, and we compute our next state value to be illegal. And then on the next clock pulse, we will go into the illegal state. And once we're in the illegal state, we won't be loading the instruction, we won't be loading any registers or anything. We'll just stay in the illegal state forever. So our system will kind of freeze up at that point. Okay, that's it for basic instruction execution. In the next video in this series, I'll be going over the system Verilog code that implements the finite state machine and the timing that we've just been talking about. And I will see you there.